So first step is to draw all of the forces acting on the 10 kilogram or whatever the weight is, and then to resolve any forces that are not in the x and y dimension, resolve those into the x and y dimension. So there are really three forces in the beginning. There's the weight, just the mass times 9.8, and then there's a tension and another tension. And these tensions are not in either the x or y dimension, so I have to resolve them into x and y components. So this would be the x component of T2, this is the y component of T2, and then this is x and y components of T1. Since I'm given this angle, to get this, I'm going to do cosine of 65 times T2, and that gives me T2y. So cosine 65 T2 is 0.423 T2. And this is the angle, so this is the opposite. This is the hypotenuse, so I use sine to get this. It ends up being 0.906 T2. Over here, here's my angle. To find the y component, I use cosine of the angle times T1, and to find the x component, since this is the opposite, I use sine of the angle times T1. Once I've got that, I just write equations for net force in the x dimension and the y dimension, and then I'll have a system of equations that I can solve using algebra. So in both dimensions, in the x dimension and the y dimension, the net force is 0. That's just using Newton's second law, net force equals ma, and if this is stationary, since static equilibrium, there's no acceleration, so net force is 0 in both dimensions. The other way to find net force is to add up the forces. So I did it with the x dimension first. There are two forces in the x dimension. There's positive T2x and negative T1x. So net force equals T2x minus T1x. So since that equals 0, then these two things are equal to one another. In the y dimension, I have three forces, T1y, T2y, and weight. These are both positive because they're up. This is down, so it's negative. So I have T1y plus T2y minus 98. And now I'm going to substitute a bunch of stuff and do a bit. So I'm taking this first, basically this equation. I've just added T1x to both sides and then flipped it around apparently. So T1x is 0.643 T1. So I plugged in 0.643 T1 there for T1x. T2x is 0.906 T2. So this came from here. So if 0.906 T2 equals 0.643 T1, I can divide both sides by 0.643, and then I get 1.41 T2 equals T1. So that's a useful ratio that I can use to substitute in later. I'll substitute this in for T1 at some point. So now taking my y equation, my y dimension equation, I'm substituting in for T1x this. Wait, sorry, that's not T1x, that's T1y. So that'd be this, 0.766, and for T2y, that'd be 0.423. So here's my new equation, 0.766 T1 plus 0.423 T2 minus 98 equals 0. And I've got two variables here in one equation, so I can't solve for anything. But if instead of T1, I put in this, then I can solve. Because I found out earlier that T1 equals that many T2s. So this and this are just the same, except instead of a T1, I put in 1.4 T2, which is the value of T1. And then I can solve for T2. So it comes out to T2 is 65.2 newtons. And to find T1, the easiest way to do it is just to use this relationship again. T1 equals 1.41 times this, which gives me 91.9. Let's see, maybe yeah.